Hello students, welcome back. We completed everything up to 3.2 part A. Now let's go to part B. We're looking at quadratic type of problem with denominator, but previously we only had numerical denominators. Denominators are 5, 10, and 4 respectively. But this time we have x expressions here, x minus 2, x plus 1, and then this humongous expression, which can be simplified as a matter of fact. Not simplified as a matter of fact, it's arguable whether this is simpler. Let me just use the term transformed. Let's transform like this. So there's 7x plus 1 over x squared minus x minus 2. Well, instead of that, no, let's not completely count it off. Let's look at the final expression. Look at the denominator. X squared minus x minus 2 is factored over, and these factors coincide with these. And then that makes the problem slightly easier, then a little bit more general. If only one of them is sharing and then there are others, then of course you're going to get something more complicated. But at some point I have to draw lines, so yeah, this is more likely to, this is a kind of thing that is likely to show up in the exam level. If there's another one, say for example, if this is not x plus 1 but x plus say 10, something like that, then that makes this problem harder, even harder, and that's unlikely to show up in the exam. Not absolutely no, but unlikely, I should say. Okay, so in this case, both of these are reproduced here. Only one of them is reproduced, and that'll make the problem harder. Okay, all right. So much for the preparation. Now let's simplify by multiplying the LCD, the least common denominator, or the least common multiple of the denominators, which is the product of those. So multiply that to the first fraction, and to the second fraction, and to the third fraction as well. So let's not worry about this one here, even though the problem came with this fashion. You can factor and then work out like this. Now, do you see appropriate simplification? Yeah, x minus 2, x minus 2, they go out. We have x plus 1. Now, x plus 1 go ahead. So we have 2, x minus 2. And here, everything goes out. We have 7x plus 1. In the right hand side, it looks like I don't need parentheses. Yeah, okay, all right. Okay, all right. All the denominators are now gone, so let's break up the parentheses. X squared plus x. And then the next parenthesis, 2x minus 4, and then 7x plus 1. And is that a quadratic equation? Yes, it is. Move everything to the left-hand side to get everything into the standard form. X squared, and we have 3x here, but minus 7x, minus 4 here, but minus 1 as well. So x squared minus 4x minus 5 equal to 0. Feel okay about this? Let's see. Like terms, 2x became 3x, and like term, negative 4 plus 1, negative 4 minus 1, negative 5. Yeah, looks like it. Looks good to me. And then factoring this, if you factor right, it is x minus 5, x plus 1, equal to 0. It's easy because this is monic trinomial. We get x is 5 or x is -1. So we get these two solutions. I just highlighted in blue, and this one I just highlighted in purple. But if you stop here, you're not going to get full credit. You still have one more work to do. Why? Put those values back into the original equation and see if it works. And that usually is the kind of checking process. That's the kind of checking process that I advise you to do every single time. But there are some problems that checking process is absolutely necessary, and there are some problems that are not really necessary if you are totally comfortable with your computation. This is one of those former, absolutely necessary, because a lot of things can go bad in the denominators. If it becomes 0, everything breaks apart. If you have a radical, then even worse thing can happen. So it is very important to plug all those things back in. In this case, not really. All the x expressions are in numerator, so if you're completely comfortable with your computation, then you can skip this checking process. In this case, you should not skip. If you plug in x equal to 5, it'll turn out okay. If you plug in x equal to -1, that's going to be a problem, because right here I have x plus 1, and we have x plus 1 here as well, and these are going to become 0. You cannot have 0 in the denominator. So this one here actually fails. This kind of solution is called an extraneous solution. Extraneous solution, so it should be counted out. I don't like the term extraneous solution, to tell the truth, because outside math classroom, how often do you use the term extraneous? I don't like it. I would much rather use this kind of term, but I'm in minority. Most textbook authors use this term extraneous, even though people never use it outside classroom. I'd much rather call it invalid solution, or illegitimate, or even fake solution. I'm going to use those kind of terms instead of what the heck is this extraneous solution. I mean, this is a kind of a strange jargon people create to sound just smarter than they actually are, at least in my opinion. Anyway, the full solution is here, and then I use the term invalid here, not extraneous. But our textbook authors use extraneous, and actually everybody uses the term extraneous. I am in minority. So whenever you have denominators, check. Whenever you have radical, that's even more important, check. Let's see, ready for another? Okay, how about this? Okay, alright. And then in this case again, you can factor this denominator, and then you're gonna end up with the other two denominators. So if one of them matches and the other one doesn't match, something like this, in that case the problem would have been a lot harder. But I have to draw a line somewhere. So if I write that kind of problem, that's going to be certainly an extra credit problem. But this kind of thing is actually pretty hard, yes, but it's still standard. So how do you do that? Well, just multiply the LCD, and then here multiply the LCD, we don't need this middle part, and then you can go ahead and do some simplification. X plus 2, they simplify each other out. X minus 1, same goes here, everything. So you have 3x times x plus 2, and then x plus 2, and then 4 minus 7x. That's it, isn't it? Let's do some alignment. So, okay, all right, no more denominators, so you can break up. So 3x squared plus 6x plus x plus 2 minus 4 plus 7x equal to 0. After flipping everything to the left hand side, I'm going to get, let's see, 3x squared and then plus 14x minus 2. Is that right? 3x squared, 14x, and negative 2. Oh, yeah, I did it wrong. This is x plus 2 and that x plus 2 cancelled out, so this should be x minus 1 and this should have been negative 3x. So instead of this, 7x, 8x minus 3 plus 5. Yeah, that would have been correct simplification. Okay, now it makes sense. I can factor it. 3x minus 1, x plus 2 equal to 0, I think. Let's see, that's positive 6 minus 1. Okay, that's going to be right. And if you're unsure, you can always go to this tic-tac-toe and get it right. So you're going to get x is 1/3 or x is negative 2, and don't forget to check your answers. It'll turn out x equals to 1/3 is a legitimate solution, but x equal to negative 2 will not work. It'll make this denominator vanish, and consequently that too. So everything becomes invalid for negative 2. Let's see, what did I do in my answer key here? Oh, I have no answer key here. Okay, in that case, okay, all right, I'll include everything here. So x is 1/3. That's the only solution. Negative 2 is not. And then as for this factorization, well, that's left to you. You can set up the tic-tac-toe and do things, or you can use alternative method. Anyway, it works this way. So we went through a number of examples on elementary equations, linear equations, and quadratic equations. But there are some exceptional problems. When x expressions are in denominator, then make sure you check those candidates of solutions to the original equation to see if that makes sense or if it is invalid. And that may be a little bit new to many students.